As one of humanity's most advanced tools for peering into deep space, James Webb may hold the key to unlocking the biggest secrets of the universe. In a remarkable study, the Supreme Observatory has shed light on a theory that could change our understanding of where we are located within the universe. Its latest data support the idea that we may be living inside a vast cosmic void, which could also help explain the long-standing Hubble tension, a dilemma that has troubled cosmologists for decades. But does it hold true? Are we truly living in a giant void? All this and more will be discussed in today's episode. In the very beginning, there was a bang. Big Bang, if you will. This massive explosion created the universe and filled it with the seeds of all the matter and energy currently present. But with that kind of turbo kickstart, growth isn't something that ends after the initial blast. The universe continues to expand, even accelerating as it goes, at a rate referred to as the Hubble constant. The Hubble constant is an incredibly important number to pin down in the field of cosmology, but it's not an easy one to suss out. In fact, it's so difficult to divine that the Hubble tension caused by our inability to land on a single number has become arguably as famous as the Hubble constant itself. And recent results from the James Webb Space Telescope have just re-cemented this tension as a very real problem to overcome. If a researcher wants to estimate the Hubble constant, they have two main avenues. There are others, of course, but the two most common are Cepheid variables and the cosmic microwave background. The cosmic microwave background is the leftover radiation still permeating the universe from the Big Bang. Using the cosmic microwave background is often likened by researchers to using a baby picture to predict what someone will look like as an adult. To some extent, knowledge about the universe's infancy should allow researchers to make predictions about its current state. Researchers have long used it to make inferences about the very beginnings of our universe and have used it to predict what the Hubble constant should be. Fairly recent cosmic microwave background calculations set the Hubble constant at around 67 kilometers per second per megaparsec, with an uncertainty of about 0.7%. But the thing about theory is that you need to test it, and when the Hubble telescope launched, it became possible to do just that. Free of the constraints of ground-based telescopes clouded by atmosphere, the Hubble telescope was able to take extremely accurate distance measurements of far-off objects. And that's where Cepheid variables come in. Cepheid variables are a type of pulsating star that falls into a category of objects called standard candles. Objects that have a measurable and consistent brightness, allowing us to fairly straightforwardly measure how far away they are. Measuring distances isn't easy in space, but it's crucial to being able to measure expansion. As convenient as it would be to stop there, there's one more step to the Cepheid method. Once their brightnesses have been divined, and we know how bright a Cepheid is that blinks at a certain rate, we use those brightnesses to calculate the brightnesses of nearby supernovae. Then, using a quality called redshift, we use those supernovae to calculate the brightnesses of other supernovae that are even farther away. Because they're much brighter, we can see supernovae at much greater distances than we can see Cepheids. And because you can see the expansion of the universe better the further away you look, we look to the far-off supernovae for the ultimate calculation. This chain of brightnesses is referred to as a distance ladder, and you can't move to one rung without first calculating all the ones that come before. Over time, the Hubble telescope clocked distances for several Cepheid variables, the first rung on that distance ladder, which in turn allowed researchers to make an experimental measurement of the Hubble constant. But instead of agreeing with the prediction, it has consistently yielded values between 72 and 74 kilometers per second per megaparsec. When experiment and theory diverge, it can mean one of two things. Either your measurement is wrong, or your theory is wrong. And that, in a nutshell, is the Hubble tension. But exactly which is wrong, the theory or the experiment? This new round of measurements from the James Webb Space Telescope seems to cement the idea that there's something wrong with the theory. Able to basically rerun Hubble's observations with a higher resolution at wavelengths, in which Hubble struggled to get clear pictures, James Webb has pretty much confirmed that Hubble wasn't seeing ghosts. It really is producing data that allow for an accurate calculation of the Hubble constant of the current universe. So, what's wrong with the theory then? Well, if you can answer that, you're light years ahead of the best astrophysicists in the business. It could have something to do with dark energy, or dark matter, or gravity. Maybe we're seeing all of the data fine, but we're somehow wrong about the fundamental nature of Cepheid variables. Kicking aside all previous speculations, a new bold study just presents one possible explanation to one for the universe's greatest discrepancies: that we live in a giant void in space. On the largest scales, the universe is uniform, with equal amounts of matter and energy everywhere. If you drew an imaginary sphere a few billion light-years wide around any point and measured the total amount of mass inside, you'd get the same number everywhere, to about 99.99% accuracy. But if your sphere were smaller, you'd start to get different numbers in different locations. Gravitation pulls matter into filaments, groups, and clusters of galaxies, and steals matter away from less dense regions, creating great cosmic voids. Today, matter in the universe is distributed like a combination of a spider web and Swiss cheese. The holes in the universe are stupendous, with some stretching tens of millions of light years across before you run into any galaxies at all. On the other hand, there are places where filaments intersect, a great nexus in the cosmic web, that correspond to the locations and existences of ultra-large galaxy clusters, some of which contain many thousands of times the mass of our galaxy. But in between scales, where there are huge density differences and those where the density averages out to the same number every time, something interesting is happening. On scales ranging from about 500 million to 3 billion light years in diameter, you might find that two different regions that look very similar on the surface, containing voids and clusters, filaments lined with galaxies, multiple Swiss cheese holes, etc., might actually differ in their overall densities by about 20% or more. Without doing a very large, detailed survey of a very large set of regions in the universe, going well beyond billions of light years, you'd have no way to know for certain whether you lived in one or not. But there would be a hint. If you lived in an overdense region, even one that looked very much like an average region in every other respect, you'd find that there would be one thing that looked weird: the expanding universe. Because you had more matter than average where you were, the galaxies nearby would mutually gravitate more forcefully, and the expansion rate of the universe would appear slower for you. If you looked to very large, distant scales, the expansion rate would appear normal again, but right where you are, you'd measure it to be lower than average. Any technique that only relied on nearby measurements, things like parallax, Cepheids, or even most supernovae, would give you that skewed result. On the other hand, if you lived in an underdense region, your local neighborhood of space would gravitate less strongly than average, and the expansion rate would appear greater or higher for you. We've noticed this exact problem in our measurements for a few years now. If we try and measure the expansion rate using these cosmic distance ladder techniques, we find that the universe expands about 5 to 10% more quickly than other methods indicate. And that seems to be an explanation the deviations in the Hubble constant. That's also why, in new study, scientists believe that the Milky Way galaxy is drifting on the edge of one of these voids in its little corner of the universe, a bubble of space known rather obviously as the local void. Previous measurements have put the size of the void at around 60 megaparsecs in size, around 200 million light-years. But that's only part of the picture. The local void may be engulfed by a far larger underdensity, some 600 megaparsecs across, known as the local hole, or Keenan-Barger-Cowie supervoid. One of the most striking anomalies associated with the local hole is the observation that galaxies in our region of space are more sparsely distributed. And that is a big deal. Within the framework of the standard lambda cold dark matter model, cosmic structures are believed to have formed from small quantum fluctuations in the early universe, amplified by the influence of dark matter. These fluctuations would grow over billions of years into the large-scale cosmic web we observe today, including voids like the local hole. However, there are some issues. The underdensity of the local hole is difficult to explain purely within the standard dark matter-based cosmology. According to simulations, such a large and deep void in this region of space is improbable within the lambda cold dark matter model. Moreover, the peculiar motion of galaxies within and around the local hole seems to suggest that the region may be gravitationally influencing cosmic flows in unexpected ways, which standard models struggle to account for. But this becomes less of a problem if we use a different model for how gravity works. It's called modified Newtonian dynamics, or MOND for short. The MOND theory, first proposed by Israeli physicist Mordechai Milgram in 1983, aims to address the rotation curves of galaxies. When observing galaxies, it became clear that stars at the outskirts of galaxies rotate much faster than expected based on the visible mass alone. In the standard model of cosmology, this discrepancy is attributed to dark matter, an invisible substance thought to constitute roughly 85% of the universe's matter. Dark matter would provide the necessary gravitational pull to explain the unexpectedly high rotational speeds of galactic outskirts. However, MOND proposes a different explanation. Instead of invoking dark matter, it suggests that Newton's laws of motion break down at very low accelerations, about 11 orders of magnitude smaller than the acceleration we experience on Earth. In regions of space where gravitational forces are extremely weak, such as the outer parts of galaxies, gravity doesn't behave as predicted by Newtonian dynamics. MOND modifies Newton's second law, introducing a new fundamental constant of acceleration below which the force of gravity decays more slowly than expected. By altering the law of gravity itself, MOND can account for the observed galactic rotation curves without the need for dark matter. Not only that, MOND provides an alternative framework for understanding gravitational behavior in regions of very low density, such as cosmic voids. By modifying Newton's law of gravity at low accelerations, MOND could provide new insights into how mass and gravity interact in these underdense regions of space. One key aspect of MOND is that it predicts different gravitational behavior in voids like the local hole compared to the predictions made by standard gravity models. In the standard model, voids are areas where gravitational forces are weak because of the lack of matter. However, in MOND, the modification of gravity at low accelerations could mean that voids like the local hole exert a stronger gravitational influence than expected. This stronger gravitational influence could help explain why galaxies around the local hole appear to be moving slower than expected. In standard cosmology, the expansion of the universe and the motion of galaxies are influenced by the distribution of dark matter. In the MOND framework, the modified gravitational dynamics in underdense regions could alter the expected cosmic flows, leading to slower galaxy velocities in and around the void. Furthermore, MOND could also explain why the local hole formed in the first place. In the standard model, the formation of large voids like the local hole is a stochastic process driven by the interplay of dark matter and cosmic expansion. However, in MOND, the dynamics of structure formation could be different due to the modified gravitational law. Voids like the local hole may form more readily or grow larger in a Mond universe, offering a potential explanation for the existence of such a large, underdense region. One of the most compelling aspects of the Mond model is that it makes testable predictions about gravitational behavior in cosmic voids. If Mond is correct, we would expect to see different patterns of galaxy motion and cosmic flows in regions like the local hole, compared to what is predicted by the standard model. In recent years, there has been increasing interest in testing Mond's predictions through observations of cosmic structures. One promising avenue for testing Mond in the context of the local hole is through detailed observations of galaxy velocities and cosmic flows in and around the void. By comparing these observations with the predictions made by both Mond and the standard model, researchers can determine which theory better explains the dynamics of this region of space. Moreover, upcoming surveys of the large-scale structure of the universe, such as those being conducted by the Vera C. Rubin Observatory, will provide more detailed maps of cosmic voids and the distribution of galaxies. These surveys will offer an unprecedented opportunity to test Mond's predictions in underdense regions like the local hole. While Mond offers an intriguing alternative to the dark matter hypothesis, it is not without its criticisms. One of the main challenges for Mond is that it struggles to explain certain large-scale phenomena, such as the cosmic microwave background radiation and the formation of galaxy clusters, which are well explained by the standard model. Mond also requires additional modifications to account for observations on larger cosmic scales, such as the introduction of relativistic extensions like tensor vector scalar theory. Another criticism of Mond is that it lacks a fully developed theoretical foundation. Unlike dark matter, which fits neatly within the framework of particle physics, Mond requires a modification of fundamental physics that has not yet been fully integrated into a broader theory of gravity. This has led some researchers to view Mond as a phenomenological model, a useful tool for explaining certain observations, but not necessarily a replacement for the standard model of cosmology. Nevertheless, Mond's ability to explain galaxy rotation curves without invoking dark matter, as well as its potential to address anomalies like the local hole, has kept it at the forefront of alternative gravity theories. As more observations of the large-scale structure of the universe become available, Mond's predictions will be put to the test, potentially providing new insights into the nature of gravity and the universe. In short, while there are significant problems with Mond, it's worth using it as a tool to try to figure out where the holes lie in our current understanding of the universe. It may be that the real answer lies somewhere close to a mix of both theories, that Einstein doesn't need to be thrown out, but expanded upon. As Dr. Indranil Banik from St. Andrews University, who was involved in the study, writes in an article for The Conversation, Einstein is thought to have said that we cannot solve problems with the same thinking that led to the problems in the first place. Even if the required changes are not drastic, we could well be witnessing the first reliable evidence for more than a century that we need to change our theory of gravity. In another remakeable study, physics discovered at last strongest missing link in black hole. There are only a few pathways that the universe has for enabling the formation of black holes in the first place. The most common mechanism is thought to come directly from massive stars that reach the ends of their life cycles. Whenever a star is fusing light elements into heavier ones, it releases energy in the form of radiation in its core, and that radiation is what holds the star up against gravitational collapse. Whenever the star's supply of those key elements starts to run low, the radiation pressure decreases and the star's core contracts and heats up. If the new high temperatures are sufficient to begin fusing the next heavier set of elements, the star's life cycle continues. If not, the central core can collapse into either a neutron star or a black hole, dependent on mass. Some stars die in spectacular core collapse supernovae, leaving black hole remnants behind from their cores. Other stars simply directly collapse, converting up to the entire mass of the progenitor star into a black hole. It's also possible, perhaps even likely, that converging cold streams of gas can create even more massive black holes, of perhaps a few thousand or tens of thousands of solar masses, particularly in the early universe. And finally, two neutron stars of sufficient masses can merge together, giving rise to a black hole post-merger. All of these mechanisms are thought to lead to the production of black holes within our universe. Moreover, over time, black holes don't just simply remain with the properties they had when they were created. They interact, merge, and devour matter that falls into them, leading to the potential for mass growth over time. Most of the black holes we know about were identified through one of two means: through the inspiral and merger of two lower mass black holes, creating a heavier, higher mass black hole at the end, or because a black hole is actively feeding on matter, either from a transient source, like devouring a gas cloud or star, or from an ongoing source, like siphoning matter off of a binary companion. In other words, most of the black holes that we actually find are discovered when they're in the process of growing and gaining mass. At the centers of galaxies, we're learning that supermassive black holes reside there. Early on in the universe, as shown by observatories like James Webb, Chandra, Hubble, and ALMA, supermassive black holes were nearly as massive as the cumulative total amount of mass in stars in those galaxies. But by the present day, they're usually only about 0.1% as heavy as the total stellar mass of a galaxy. That gives us an interesting set of places to look for these in-between black holes' masses that are more massive than black holes arising from individual stars, but less massive than the supermassive behemoths, either at the centers of small, low-mass galaxies or deep inside the central cores of globular clusters. This latter option, of looking inside globular clusters for intermediate mass black holes, has been the subject matter of many searches over recent decades by astronomers. Globular clusters have many advantages in this quest. That provides an excellent set of motivations for scouring globular clusters, and in particular, the centers of globular clusters, for the possibility of housing intermediate mass black holes. Searches have been conducted using millisecond pulsars as tools, noting that populations of these pulsars, which are very accurate clocks, would experience jerks and jounces in their timing. Simulations predict that intermediate mass black holes should indeed form in globular clusters, with masses greater than 100 solar masses, but below 100,000 solar masses. Using a proposed but not yet built tool such as the Next Generation Very Large Array, scientists could be sensitive to intermediate mass black holes in globular clusters around galaxies located up to 80 million light-years away. And globular clusters, Messier 62 and Messier 22, were both shown to have black holes within them, but of the stellar mass, rather than intermediate mass, variety. However, it was a globular cluster located on the outskirts of our galaxy, and instead bound to the Sagittarius dwarf galaxy, Messier 54, that gave us our first indication of an intermediate mass black hole at the center of a globular cluster. By noting the motions of many stars near the globular center's core, astronomers concluded there was a strong likelihood of a black hole of around 9,400 solar masses, suggesting that these missing link black holes did indeed exist. However, much like other intermediate mass black hole candidates, the evidence has always been fairly inconclusive. The definitive evidence ruling out alternative explanations has thus far been lacking. However, two new studies published on 2024 finally give us the evidence we need to declare discovery when it comes to intermediate mass black holes. The key object is indeed globular cluster Omega Centauri, the most massive globular cluster known within the Milky Way galaxy and one long suspected to contain an intermediate mass black hole. Located a meager 17,000 light-years away, its vital stats are that it has a radius of roughly 75 light-years, has a total mass of around 4 million solar masses, and is estimated to contain around 10 million stars. Unlike most globular clusters, which are thought to have originated from a major episode of star formation from a much more massive cloud of gas than typically creates open star clusters, something akin to what we're seeing occurring right now in the Tarantula Nebula, there's substantial evidence that Omega Centauri took a much more uncommon path toward becoming a globular cluster, that it instead is the remnant core of a largely destroyed dwarf galaxy that was gobbled up by the Milky Way long ago. Unlike globulars formed from superstar clusters, Omega Centauri's low abundance of heavy elements, its motion through the Milky Way, and its somewhat young age of only 11.5 billion years for a globular cluster, combined with a complex variety of stellar populations found within it, all suggest this unusual origin for this object. But how would we determine whether this globular cluster, or for that matter, any nearby globular cluster, actually contains an intermediate mass black hole within it or not? The key is to obtain tremendous amounts of high-quality data about the stars located within the globular cluster itself, including about the motion of those stars over time. Many of us remember seeing the spectacular images of the event horizons of the supermassive black holes at the center of the Milky Way, Sagittarius A, as well as the one at the center of Messier 87, about 2,000 times farther away, but also about 1,500 times as massive as the one at the center of our own galaxy. Although this is often treated as the smoking gun evidence for these supermassive black holes, there were two lines of evidence that were surefire giveaways before we actually acquired those measurements. One line of evidence was the strong X-ray and radio emissions coming from these galactic centers, something seen emanating from supermassive black holes all across the universe. The large angular features, owing mostly to the close proximity of these black holes to us, were joined by flares and/or jets, revealing a likely black hole. But even more compelling was the fact that we had tracked the motions of a large number of stars within the Milky Way's center over many years, and they were all shown to be orbiting a common point from which no light was emitted. Just by understanding gravity, we could not only infer the presence of a black hole at the Milky Way's center, but we could infer its mass as well. While a galaxy like Messier 87 is too far away to measure the orbits of individual stars near its center, that obstacle poses no problem for a globular cluster like Omega Centauri. At 17,000 light-years distant, it's actually about 10,000 light-years closer than the stars orbiting the black hole, Sagittarius A, at the Milky Way's center. A Herculean project was taken on to measure the proper motions of the stars within it, specifically the stars near the globular cluster's center, over baselines of around 20 years, using the best data available to humanity over those timescales, from the Hubble Space Telescope. In addition to this proper motion data, photometric data was taken of these stars as well, enabling astronomers to measure properties like their color, magnitude, and also to sort them by stellar population. More than 1 million stars were measured within Omega Centauri in this fashion over those long baselines, as catalogued in the two recent studies led by Maximilian Heberle and Nadine Neumeier. Unlike previous studies, these new papers, after sifting through all 1.4 million stars catalogued, identified 7 smoking gun stars that all appear to have been kicked to speeds beyond the cluster's projected escape velocity, something that can only be explained by being bound to a massive black hole. What's remarkable about many of the images used to reconstruct the motions of these stars is that they weren't acquired with any particular science goal in mind. They were mainly taken in order to facilitate the Hubble Space Telescope in calibrating its instruments. But just like many of the first James Webb's images, primarily used for calibration purposes, yielded an enormous amount of bonus science. The observations helped astronomers track myriads of these stars over very long periods of time. With Hubble's remarkable resolution, especially at shorter wavelengths, even the rich star fields of Omega Centauri could be easily resolved into individual objects. The fact that multiple hypervelocity stars were found indicates that they aren't just experiencing a momentary gravitational interaction with a companion or a nearby interloper, but rather that there must be a concentrated mass nearby that they're very likely gravitationally bound to. Just as the stars within the Milky Way's galactic center can get up to remarkable speeds based on how tightly bound they are to the central black hole, the 7 identified hypervelocity stars within the very central region of Omega Centauri reveal a black hole as well. Even with the lack of precise orbital data for these stars, the scientists involved in the study were still able to place a remarkable lower limit on the mass of the black hole inside, 8,200 solar masses. That figure of 8,200 solar masses is more than a factor of 30 heavier than the heaviest stellar mass black hole known, and yet is more than a factor of 30 lighter than the lightest supermassive black hole known. For a long time, astronomers have wondered something like, if there really is an intermediate mass black hole in these globular clusters, then where are the hypervelocity stars? The discovery of not just 1 or 2, which might be unrelated interlopers, but 7 all located within the innermost arc-second of sky, is that smoking gun evidence we need to declare the discovery of an intermediate mass black hole. There is no other explanation that's compatible with the known laws of physics. However, we have to keep a limitation in mind. This black hole, at such a smaller mass than the one at the Milky Way's center, will require very long periods of time, roughly a century, rather than roughly a decade, to map out the complete orbits of these fast-moving stars that revolve around them. However, forthcoming James Webb's data should precisely measure the line-of-sight velocity of these stars to better precision than Hubble ever could, and long-term studies with ground-based facilities could begin to determine how these stars accelerate. At long last, we've found our first surefire intermediate mass black hole, and now the follow-up quest to pin down its exact properties begins. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. From the neighborhood to the edge of time, the James Webb Space Telescope challenged our understanding of the cosmos and showed the universe in a way no other telescope in the past could. And in a recent remarkable observation, the $10 billion Infrared Space Observatory has focused on Mercury, which should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. And now, by using powerful telescopes like James Webb, scientists have once again lifted the veil on the secrets of the planet, revealing Mercury is not what we think. Join us as we shed light on the most enduring mysteries of the innermost planet in our solar system. Mercury is the closest planet to the Sun, orbiting at an average distance of about 57.9 million kilometers. With a diameter of just 4,880 kilometers, it is the smallest planet in the solar system, slightly larger than Earth's moon. Despite its proximity to the Sun, Mercury's surface temperatures vary dramatically, ranging from scorching highs of 430 degrees during the day to freezing lows of 180 degrees at night. Mercury's orbit is highly eccentric, meaning it is not a perfect circle, but rather an elongated ellipse. This eccentricity, combined with its rapid orbital period of just 88 Earth days, leads to fascinating orbital dynamics that have intrigued astronomers for centuries. One of the most notable features of Mercury's orbit is its 3-2 spin-orbit resonance, where the planet rotates 3 times on its axis for every 2 orbits around the Sun. The surface of Mercury is a stark, barren landscape, characterized by numerous impact craters, vast plains, and towering cliffs. The planet's surface bears the scars of a violent history, with craters ranging in size from tiny pits to massive basins hundreds of kilometers across. The largest of these is the Caloris Basin, a massive impact crater over 1,500 kilometers in diameter, formed by a colossal collision with an asteroid or comet billions of years ago. Mercury's surface is also home to a network of long, steep cliffs known as Lobat scarps. These scarps are thought to have formed as the planet's interior cooled and contracted, causing the crust to buckle and fracture. Some of these cliffs rise as high as 3 kilometers and stretch for hundreds of kilometers across the planet's surface. Despite its barren appearance, Mercury's surface is not entirely devoid of activity. Recent observations have revealed evidence of volcanic activity in the planet's past, with smooth plains and ancient lava flows suggesting that Mercury once had a more geologically active history. However, unlike Earth or Venus, Mercury's volcanic activity appears to have ceased billions of years ago, leaving behind a frozen, lifeless landscape. One of the most puzzling aspects of Mercury is its magnetic field. Mercury is the only terrestrial planet besides Earth to have a global magnetic field, although it is much weaker than Earth's. The existence of this magnetic field was first confirmed by NASA's Mariner 10 spacecraft in the 1970s, but its origin remains a mystery. A planet's magnetic field is typically generated by the motion of molten iron within its core, a process known as the dynamo effect. However, given Mercury's small size and proximity to the Sun, scientists were surprised to find that the planet still has an active dynamo. Theories suggest that Mercury's core may contain a higher proportion of iron than previously thought, or that the planet's core has a unique composition or structure that allows it to sustain a magnetic field. Adding to the mystery is the fact that Mercury's magnetic field is not symmetrical. It is significantly stronger in the northern hemisphere than in the southern hemisphere, a phenomenon that is not yet fully understood. Some scientists believe that this asymmetry may be due to variations in the planet's core or mantle, while others suggest that it could be a result of interactions between the magnetic field and the solar wind. What's more, unlike Earth, Mercury has no significant atmosphere. Instead, the planet is surrounded by an extremely thin layer of atoms known as an exosphere. This exosphere is composed primarily of oxygen, sodium, hydrogen, helium, and potassium, and is constantly replenished by the solar wind, micrometeoroid impacts, and the release of volatile materials from the planet's surface. The existence of Mercury's exosphere was first confirmed by Mariner 10 and later studied in greater detail by NASA's Messenger spacecraft. The exosphere is so tenuous that it is barely detectable, with an atmospheric pressure less than a trillionth of Earth's. Despite its thinness, the exosphere plays a crucial role in the planet's interaction with the solar wind and the space environment. One of the most fascinating aspects of Mercury's exosphere is its dynamic nature. The atoms in the exosphere are constantly being stripped away by the solar wind, only to be replaced by new atoms from the surface. This continuous exchange of particles creates a delicate balance that can be easily disrupted by solar activity, leading to fluctuations in the composition and density of the exosphere. Mercury's most striking feature is its unusually large core, which makes up about 85% of the planet's radius. This core is believed to be composed primarily of iron, with smaller amounts of nickel and other elements. The sheer size of Mercury's core relative to its overall size is unique among the terrestrial planets and has led to much speculation about the planet's formation and history. One of the leading theories suggests that Mercury may have once been a much larger planet, with a thick rocky mantle similar to Earth's. However, a giant impact early in the planet's history could have stripped away much of this mantle, leaving behind the dense metallic core we see today. This giant impact hypothesis is supported by the planet's high density and the relative scarcity of silicate materials on its surface. The core of Mercury is also thought to be partially molten, which may explain the planet's magnetic field. But the exact state of the core, whether it is completely liquid, partially solid, or something in between, remains an open question. Understanding the nature of Mercury's core could provide valuable insights into the formation and evolution of the inner planets in our solar system. However, given its proximity to the Sun and the extreme conditions on its surface, Mercury is a challenging planet to study. Mercury has been visited by only 2 spacecraft, NASA's Mariner 10 and Messenger missions. These missions have provided the bulk of our current knowledge about the planet, but what is really interesting about Mercury are the things that can't be seen. And now, thanks to incredible research efforts, scientists have finally given us some remarkable clues that could upend our understanding of this enigmatic world. In a groundbreaking revelation, scientists have discovered that Mercury, the innermost planet in our solar system, may harbor salt glaciers that could support life beneath its sun-scorched surface. This discovery is not only a significant leap in our understanding of the planet's geology, but also raises intriguing possibilities about the potential for life in environments once deemed inhospitable. The key to this new discovery lies in the data gathered by NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger's suite of scientific instruments provided unprecedented insights into the planet's surface composition, magnetic field, and geological history. One of the most surprising findings from Messenger's mission was the detection of unusual surface features that suggested the presence of volatile substances, including water ice and salts. Researchers have long known that Mercury's poles contain deposits of water ice, trapped in permanently shadowed craters. These craters, located in the planet's polar regions, are shielded from the sun's harsh rays, allowing ice to accumulate and persist. However, the discovery of salt glaciers has added a new dimension to our understanding of Mercury's polar deposits. Analysis of Messenger's data revealed features that resemble glaciers on Earth, but with a twist. These so-called salt glaciers are formed from a mix of salts, such as sodium chloride and magnesium sulfate, and ice. The presence of these salt deposits suggests that, at some point in Mercury's history, liquid water may have been present on the planet's surface and subsequently evaporated, leaving behind these saline features. The formation of salt glaciers on Mercury involves several stages. First, volatile compounds such as water and various salts were likely present in the planet's crust. Over time, geological processes, including impacts and volcanic activity, would have brought these materials to the surface. When Mercury's surface temperatures fluctuated, especially in the shadowed regions near the poles, water ice could have formed and mixed with salts. The persistence of these salt glaciers is indicative of a complex climatic history. The planet's axial tilt is minimal, meaning that its poles receive very little direct sunlight. This, combined with the extremely low temperatures in the shadowed craters, has allowed these glaciers to remain relatively stable over geological timescales. The discovery of salt glaciers on Mercury prompts a re-evaluation of the planet's potential to support life. While the current conditions on Mercury are inhospitable to life as we know it, The presence of salts and ice raises the possibility that microbial life could exist in subsurface environments, similar to how life is hypothesized to survive beneath the icy crusts of moons like Europa and Enceladus. In addition to the presence of water ice and salts, the idea that Mercury once had a more temperate climate further fuels speculation about its potential for life. If liquid water was once stable on the surface, it opens up the possibility that life could have had a chance to develop during that period. Even if no evidence of life is found, these findings can provide valuable insights into the planet's geological history and the processes that shaped its surface. Another remarkable discovery: recent scientific research has unveiled a breathtaking possibility. Mercury might be hiding a treasure trove unlike anything we could have imagined, a diamond layer 15 kilometers thick. To understand how Mercury could host such an incredible deposit of diamonds, we first need to appreciate the planet's unique geological and environmental conditions. As told, Mercury is a planet of extremes. With temperatures fluctuating from a blistering 400 degree during the day to a bone-chilling 180 degrees at night, the surface is subject to tremendous thermal stress. This temperature variation alone suggests that the planet's surface could be a breeding ground for complex chemical reactions. Additionally, Mercury's lack of a substantial atmosphere, unlike Earth's thick blanket of air, leaves it exposed to the harsh solar wind, a constant stream of charged particles from the sun. These factors combine to create an environment where only the toughest materials can endure. This leads us to the key ingredient in our story: carbon. We all know that carbon is an essential element in the formation of diamonds. Under the right conditions, extreme pressure and temperature, carbon atoms can rearrange themselves into a crystal structure, creating diamonds. On Earth, diamonds are formed deep within the mantle, where pressures are immense. They are then brought to the surface through volcanic eruptions encapsulated in kimberlite pipes. But Mercury's formation and evolution took a different path. Recent studies suggest that Mercury's formation was marked by a cataclysmic event. During the early days of the solar system, a massive impact stripped away much of Mercury's outer layers, leaving it with an unusually large core relative to its size. This event could have also compressed large amounts of carbon deep within the planet, creating conditions ripe for diamond formation. Unlike Earth, where tectonic activity and erosion constantly reshape the surface, Mercury's geological activity is limited. This means that any diamonds formed in its early history could have remained largely undisturbed, accumulating over billions of years to form a thick layer. The idea of a 15-kilometer thick diamond layer on Mercury might sound like science fiction, but it's grounded in solid scientific principles. If Mercury's early history did involve massive impacts and intense pressure, it's plausible that much of the planet's carbon was converted into diamonds. Over time, as Mercury cooled and solidified, these diamonds could have settled into a stable layer beneath the surface. Moreover, Mercury's proximity to the Sun means it has been bombarded with meteoroids for billions of years. These impacts could have further driven carbon deep into the planet's crust, adding to the growing diamond reservoir. Some scientists hypothesize that the upper crust of Mercury could be a mix of regolith and diamond-rich rock, with the diamonds concentrated at deeper levels where pressures were once highest. One might wonder how such an extraordinary claim could be substantiated. The challenge lies in the fact that Mercury is not an easy planet to study. Its proximity to the Sun makes it difficult for telescopes to observe, and sending spacecraft to Mercury presents its own set of challenges. However, the Messenger spacecraft, which orbited Mercury from 2011 to 2015, provided a wealth of data that has since been analyzed to offer clues. Messenger's X-ray and gamma-ray spectrometers detected higher than expected levels of carbon on Mercury's surface, particularly in certain regions. This carbon, found in the form of graphite, could be the remnant of a once more extensive carbon layer that has since been weathered down by meteoroid impacts and solar wind. If graphite exists in significant quantities, It strengthens the case for diamonds lying beneath, as graphite and diamond are different forms of carbon. Moreover, the high radar reflectivity observed in some of Mercury's craters is another piece of evidence. Radar signals bounce back strongly from highly reflective surfaces, such as ice or metal. However, diamonds are also excellent reflectors of radar waves, meaning that these bright spots on Mercury's radar map could be hinting at diamond-rich areas. Regardless, to fully understand the implications of these discoveries, future missions to Mercury are crucial. The next major mission to Mercury is Bepi-Colombo, a joint mission between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Launched in October 2018, Bepi-Colombo is currently en route to Mercury, with its arrival scheduled for December 2025. This mission is named after Giuseppe Bepi Colombo, an Italian scientist who first explained the relationship between Mercury's rotation and its orbit around the Sun. Bepi-Colombo consists of two spacecraft, the Mercury Planetary Orbiter, or MPO, developed by ESA, and the Mercury Magnetospheric Orbiter, or MMO, developed by JAXA. The two spacecraft will work in tandem to study Mercury's surface, interior, exosphere, and magnetosphere in unprecedented detail. The MPO will focus on the planet's surface and interior, mapping its topography, composition, and geological features, while the MMO will study the planet's magnetosphere and its interaction with the solar wind. One of the key objectives of Bepi-Colombo is to build on the discoveries made by MESSENGER and answer some of the lingering questions about Mercury. For example, Bepi-Colombo will investigate the origin of Mercury's magnetic field, which is much weaker than Earth's, and is likely generated by a partially molten core. The mission will also study the composition of the planet's surface, including the mysterious hollows, bright, shallow depressions that appear to be unique to Mercury. In addition to its scientific goals, Bepi-Colombo will test advanced technologies that could be used in future missions to Mercury and other planets. For example, the mission's solar electric propulsion system, which uses ionized xenon gas to generate thrust, could pave the way for more efficient space travel in the future. While Bepi-Colombo represents the next significant step in Mercury exploration, scientists are already looking ahead to future missions that could build on its findings. These missions could take various forms, from orbiters and landers to sample return missions, and even human exploration. One of the most exciting prospects for future Mercury exploration is the idea of sending a lander to the planet's surface. A lander would provide an unprecedented opportunity to study Mercury's geology up close, analyze its surface composition, and conduct experiments that are not possible from orbit. For example, a lander could drill into the surface to study the planet's interior structure or deploy instruments to measure the heat flow from the interior to the surface, which could provide clues about the planet's thermal evolution. However, designing a lander capable of surviving Mercury's extreme conditions presents significant challenges. The lander would need to be equipped with a sophisticated thermal control system to protect it from the intense heat of the sun, as well as radiation-hardened electronics to withstand the harsh environment. Additionally, landing on Mercury's surface is no easy feat, given the planet's low gravity and lack of atmosphere, which makes it difficult to slow down the descent. Despite these challenges, there have been several proposals for Mercury lander missions. One such proposal is the Mercury Surface Element, also known as MSE, a concept developed by ESA as part of the Bepi-Colombo mission. Although the MSE was ultimately not included in the mission, the concept could serve as the basis for future lander missions. Another proposal is the Mercury Lander Mission concept, developed by NASA's Jet Propulsion Laboratory, or JPL, which envisions a lander equipped with a suite of scientific instruments to study the planet's surface and interior. Another ambitious goal for future Mercury exploration is the return of samples from the planet's surface to Earth. A sample return mission would allow scientists to conduct detailed analyses of Mercury's surface material in laboratories on Earth, providing insights that are not possible with remote sensing or in situ measurements. For example, scientists could study the isotopic composition of Mercury's rocks to learn more about the planet's formation and evolution, or search for traces of volatile elements that could shed light on the history of water on the planet. Designing a sample return mission to Mercury poses several technical challenges. The spacecraft would need to carry a lander capable of collecting samples, as well as a return vehicle to bring the samples back to Earth. The mission would also need to overcome the challenges of operating in Mercury's extreme environment, as well as the difficulties of launching a spacecraft from the planet's surface. Despite these challenges, advances in technology and lessons learned from previous sample return missions, such as NASA's OSIRIS-REx mission to the asteroid Bennu, could make a Mercury sample return mission feasible in the future. While human exploration of Mercury is still a distant prospect, it is not entirely out of the realm of possibility. Advances in space technology, such as nuclear thermal propulsion and advanced life support systems, could one day make it possible for humans to visit Mercury and conduct scientific research on the planet's surface. Human missions to Mercury would likely be similar in scope to the Apollo missions to the Moon, with astronauts landing on the surface for short durations and conducting experiments before returning to Earth. Human exploration of Mercury would offer several unique opportunities for scientific research. For example, astronauts could conduct geological surveys of the planet's surface, study its magnetic field and interaction with the solar wind, and search for signs of past or present water. Additionally, human missions to Mercury could serve as a stepping stone for future exploration of other planets in the inner solar system, such as Venus or Mars. The future missions to Mercury have the potential to revolutionize our understanding of the planet and its place in the solar system. By studying Mercury's surface, interior, atmosphere, and magnetosphere in greater detail, scientists hope to answer key questions about the planet's formation and evolution, its geological history, and its interaction with the Sun. One of the key scientific objectives of future Mercury missions is to understand the planet's unique composition. Mercury has a much higher metal content than any other planet in the solar system, with a large iron core that makes up about 85% of its radius. This unusual composition has led scientists to propose several theories about Mercury's formation, including the possibility that the planet was once much larger and lost much of its outer layers in a giant impact. Future missions could provide the data needed to test these theories and determine the true origin of Mercury's composition. Another important objective is to study Mercury's magnetic field and its interaction with the solar wind. Unlike Earth, Mercury's magnetic field is weak and highly variable, with frequent reconnection events that create intense bursts of radiation near the planet's surface. By studying these phenomena in greater detail, scientists hope to gain insights into the dynamics of planetary magnetic fields and their role in protecting planets from solar radiation. Future missions could also shed light on the history of water on Mercury. Although the planet is thought to be too hot for liquid water to exist on its surface, MESSENGER discovered evidence of water ice in permanently shadowed craters at the poles. Bepi Colombo and future missions could study these ice deposits in greater detail, potentially revealing clues about the sources of water in the inner solar system and the history of volatiles on Mercury. Finally, future missions to Mercury could help answer fundamental questions about the formation and evolution of the solar system, and by extension, offer clues about the conditions that led to the formation of Earth and other terrestrial planets. One of the most intriguing aspects of Mercury is its unusually high metal content. The planet has an iron-rich core that accounts for about 85% of its radius, which is proportionally much larger than Earth's core. This composition suggests that Mercury experienced a different formation and evolutionary history compared to the other terrestrial planets. Understanding why Mercury is so metal-rich could shed light on the processes that influenced planetary formation in the early solar system. There are several hypotheses about Mercury's high metal content. One theory suggests that Mercury might have formed from material that was metal-rich from the beginning, possibly as a result of the Sun's early influence. Another hypothesis proposes that Mercury originally had a silicate-rich mantle similar to Earth's, but a massive impact during its formation stripped away much of this mantle, leaving behind a metal-rich core. Studying Mercury in detail could help scientists determine which of these scenarios is more accurate, providing insights into the conditions that existed in the inner solar system during its formation. Mercury is the only other terrestrial planet besides Earth that has a significant magnetic field, although it is much weaker than Earth's. The presence of this magnetic field suggests that Mercury has a partially molten outer core, which generates the field through the dynamo effect. By studying Mercury's magnetic field, scientists can learn more about the planet's core dynamics and how its magnetic field has evolved over time. Understanding Mercury's magnetic field could also provide clues about the early magnetic history of Earth. Earth's magnetic field is crucial for protecting our planet from solar and cosmic radiation, making it a key factor in the development and sustenance of life. By comparing Earth's magnetic field with Mercury's, scientists can gain a better understanding of the factors that influence magnetic field generation in terrestrial planets and how these fields evolve. This knowledge could also help scientists predict the future behavior of Earth's magnetic field, which is currently weakening. Mercury's surface is heavily cratered, similar to the Moon, but it also has unique features such as large cliffs or lobate scarps that run for hundreds of kilometers. These scarps are thought to have formed as Mercury's core cooled and contracted, causing the planet's surface to shrink and buckle. The presence of these scarps suggests that Mercury's geological history is still active, albeit at a much slower rate than on Earth. Studying Mercury's surface features can provide insights into the planet's geological history and the processes that have shaped its surface over billions of years. For instance, understanding the formation of lobate scarps can help scientists learn more about the thermal evolution of Mercury's core and mantle. This, in turn, can offer clues about the thermal histories of other terrestrial planets, including Earth. Mercury also has regions known as smooth plains, which are believed to be the result of ancient volcanic activity. The presence of these plains suggests that Mercury had a more geologically active past than previously thought. By studying the volcanic history of Mercury, scientists can learn more about the planet's internal heat generation and how it has changed over time. This information could be valuable for understanding the volcanic history of Earth and other terrestrial planets, as well as the role of volcanism in planetary evolution. Mercury has a tenuous atmosphere, or exosphere, composed mainly of hydrogen, helium, oxygen, sodium, and potassium. Unlike Earth's thick atmosphere, Mercury's exosphere is constantly being replenished by particles from the solar wind, surface interactions, and outgassing from the planet's interior. Studying Mercury's exosphere can provide valuable information about the interactions between the solar wind and planetary surfaces. The study of Mercury's exosphere is particularly important because it offers a unique opportunity to observe how a planet's surface and atmosphere interact with the solar wind. Since Mercury is so close to the Sun, it experiences much stronger solar wind conditions than Earth. By understanding how Mercury's exosphere responds to these conditions, scientists can gain insights into the processes that shape planetary atmospheres in general. This knowledge can also be applied to Earth, helping scientists better understand how our planet's atmosphere interacts with the solar wind, and how this interaction has influenced Earth's evolution. Mercury's unique characteristics challenge many existing models of planetary formation. Traditional models suggest that terrestrial planets formed from the gradual accumulation of planetesimals in the protoplanetary disk. However, Mercury's high metal content, weak magnetic field, and unusual surface features suggest that its formation involved processes that are not fully explained by these models. Studying Mercury in greater detail can help scientists refine these models and develop new theories about planetary formation. For example, understanding why Mercury has such a large iron core relative to its size could provide insights into the role of giant impacts in planetary formation. Similarly, studying Mercury's magnetic field and geological history can help scientists develop more accurate models of how terrestrial planets evolve over time. Mercury offers a unique opportunity for comparative planetology, the study of planets by comparing their properties and histories. By comparing Mercury with Earth, scientists can identify similarities and differences that provide insights into the process that shaped both planets. For instance, both Mercury and Earth have metallic cores and magnetic fields, but the differences in their sizes, compositions, and geological histories can help scientists understand the factors that influence planetary evolution. One key area of comparative planetology is understanding the role of size in planetary evolution. Mercury is much smaller than Earth, which has significant implications for its thermal evolution, magnetic field generation, and geological activity. By studying these differences, scientists can learn more about how a planet's size influences its evolution and what this might mean for Earth. Another area of interest is the study of planetary atmospheres. While Earth has a thick atmosphere that supports life, Mercury's exosphere is extremely thin and constantly influenced by the solar wind. Comparing these two atmospheres can provide insights into the factors that determine atmospheric retention and composition, which are crucial for understanding the conditions necessary for life. Mercury's proximity to the Sun and its unique characteristics make it a valuable target for studying the early solar system's evolution. The planet's high metal content, weak magnetic field, and unusual surface features suggest that it has experienced processes that are not fully understood and that may have been more common in the early solar system. By studying Mercury, scientists can gain insights into the processes that influence the formation and evolution of the solar system as a whole. For example, understanding Mercury's formation and evolution could provide clues about the distribution of materials in the protoplanetary disk, the role of giant impacts in planetary formation, and the thermal histories of terrestrial planets. These insights could also help scientists better understand the conditions that led to the formation of Earth and other habitable planets. In short, while Mercury is a small planet with a big story to tell, its unique characteristics make it a key target for understanding the formation and evolution of the solar system, including Earth. By studying Mercury's composition, magnetic field, geological history, and exosphere, scientists can gain valuable insights into the processes that shaped our planetary neighborhood. These insights can help refine existing models of planetary formation and evolution, providing a clearer picture of how Earth and other terrestrial planets came to be. As we continue to explore Mercury, we are likely to uncover even more secrets about the early solar system and the forces that shape the world we live on today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. For as long as humanity has looked up at the stars, we've wondered about the origins of the universe. How did everything come into existence? For decades, the Big Bang Theory provided a satisfying answer. This powerful explosion, which took place around 13.8 billion years ago, is thought to have set in motion the expansion of the universe as we know it. But now, with the launch of James Webb, a new frontier in space exploration opened up, and with it, an unsettling glimpse into what may have occurred before the Big Bang itself. The revelations have shaken the scientific community and sparked profound existential questions about the nature of reality and the universe we inhabit. Join us as we dig deep into how James Webb just unlocked the biggest cosmic mystery. For decades, the Big Bang theory stood as the cornerstone of cosmology, offering a comprehensible narrative of how the universe came into being. According to this theory, about 13.8 billion years ago, the universe began as a singularity, an infinitely dense point that contained all the matter and energy of what would become the universe. This state was unstable, leading to a massive expansion we call the Big Bang. Contrary to popular belief, this wasn't an explosion in space, but rather the rapid expansion of space itself. In the first tiny fraction of a second after the Big Bang, the universe was a seething hot mass of particles and energy. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to separate. This period is often referred to as cosmic inflation, where the universe expanded exponentially, smoothing out space and setting the stage for galaxies and stars to form. As the universe cooled, particles like quarks and gluons began to form protons and neutrons, which later combined to create atoms. Hydrogen and helium, the lightest elements, emerged about 300,000 years after the Big Bang during a period called recombination, when the universe became transparent to light. The leftover radiation from this event is known as the cosmic microwave background, which we can still detect today. Over the next billions of years, gravity pulled together clouds of hydrogen and helium, forming the first stars and galaxies. Inside stars, nuclear fusion created heavier elements like carbon, oxygen, and iron. When massive stars exploded in supernovae, they scattered these elements across space, seeding future generations of stars, planets, and eventually life as we know it. However, despite its widespread acceptance, the Big Bang theory has always been haunted by unresolved questions. As told, at the heart of the Big Bang theory is the concept of a singularity, a point where the laws of physics as we understand them break down. This singularity represents an infinitely small and dense state from which the universe is said to have emerged. However, the idea of a singularity itself presents profound challenges. The notion of infinite density and zero volume defies our conventional understanding of space and time, suggesting that our current physical theories, including general relativity and quantum mechanics, are incomplete. And one of the most tantalizing questions that arise from the Big Bang theory is what caused the Big Bang? What existed before it? Was there even a before, given that time and space supposedly began at that moment? While these questions have been largely theoretical, recent findings from the James Webb Space Telescope have given us new and deeply disturbing clues. Launched in December 2021, the Webb telescope has been equipped with cutting-edge infrared capabilities, allowing it to peer deeper into the cosmos than any previous telescope. Where the Hubble Space Telescope could only glimpse at faint traces of distant galaxies, James Webb can capture the earliest light emitted by the first stars and galaxies, giving us an unprecedented view into the very fabric of space-time. But Webb's capabilities extend beyond simply observing early galaxies. It can also capture data about the universe's structure, composition, and evolution in ways previously unimaginable. As scientists analyzed the data streaming in from Webb, they began to notice something peculiar, something that didn't fit within the framework of the Big Bang theory. One of the most stunning discoveries made by James Webb is its detection of structures in the early universe that should not, by all accounts, exist. Observing galaxies that are thought to have formed just a few 100 million years after the Big Bang, astronomers have encountered mature, well-organized galaxies that challenge our understanding of cosmic evolution. These galaxies seem far too old and complex for the timeline provided by the Big Bang model, which suggests that the early universe should have been a chaotic, turbulent place, with galaxies still in their infancy. What's even more alarming is Webb's observation of faint cosmic ripples, traces of energy that seem to date back to a time before the Big Bang. These ripples could be the remnants of a pre-existing universe, something that existed before the event we've come to understand as the beginning of time itself. If this is the case, it suggests that the Big Bang may not have been the true beginning, but rather a transition, a new phase in an eternal cycle of cosmic destruction and rebirth. What's notable, the idea that there might have been something before the Big Bang is not entirely new. Various theoretical models have posited the existence of a multiverse, suggesting that our universe is just one of many universes, each with its own physical laws and properties, in a vast multiverse. In this model, the Big Bang could have been the result of a local event in a larger multiverse, with other universes constantly being born through similar processes. This could involve mechanisms like eternal inflation, where different regions of space experience continuous cosmic inflation, each giving rise to a new universe. The multiverse concept offers the possibility that before the Big Bang, there were other universes or cosmic regions that existed and gave rise to our own. Another theory is the idea of a cyclic universe, where the universe goes through infinite cycles of expansion and contraction. In this model, the universe could have experienced multiple Big Bangs and Big Crunches. After expanding for billions of years, the universe could collapse back into a singularity, the Big Crunch, only for another Big Bang to occur and begin a new cycle. This concept has been explored in various forms, from ancient cosmological ideas to modern versions like conformal cyclic cosmology, proposed by physicist Roger Penrose. However, Webb's data brings a disturbing new dimension to these theories. If the faint cosmic ripples it has detected are indeed traces of a pre-Big Bang universe, then we are faced with a chilling possibility. The universe may be caught in an endless loop of destruction and renewal, where everything that exists is destined to be obliterated, only to be reborn again in a new form. This raises questions about the very nature of existence. Are we living in a universe that is fated to collapse, with all matter, life, and consciousness erased, only to be replaced by something else? The concept of eternal cycles of cosmic death and rebirth may sound philosophical, but Webb's observations lend it a disturbing degree of scientific credibility. We may be part of a universe that is not unique or special, but merely one in an infinite series, with countless others having come before and countless more to follow. The realization that our universe, and by extension, everything within it, is impermanent, subject to a cosmic reset, is nothing short of terrifying. One of the most unsettling aspects of Webb's discoveries is the suggestion that time itself may not be linear. According to our current understanding of physics, time began with the Big Bang. But if there was something before it, what does that say about the nature of time? Some theorists have begun to speculate that time might be cyclical rather than a straight line. In this scenario, the concept of before and after becomes meaningless, and the universe may be in a perpetual state of becoming, constantly evolving through an infinite loop. From the moment we are born, our understanding of reality is deeply intertwined with the flow of time. We sense its passage as a series of events, moving from the past through the present into the future. However, this perception is not necessarily an accurate representation of how the universe operates. In the early 20th century, Albert Einstein revolutionized our understanding of time with his theory of relativity. He demonstrated that time is not a constant, as Isaac Newton had previously assumed, but is flexible and relative, depending on the observer's velocity and the presence of massive objects. This discovery revealed that time and space are woven together into a four-dimensional fabric known as spacetime. This means that time does not flow uniformly for all observers. A clock on Earth, for example, runs at a slightly different rate than a clock on a satellite in orbit. The faster you travel, the slower time passes relative to someone at rest, a phenomenon known as time dilation. Yet, relativity still treats time as something that exists, even if it is flexible and malleable. More radical ideas suggest that time might not exist at all, at least not in the way we commonly experience it. In quantum mechanics, the very nature of time becomes even more puzzling. Quantum mechanics deals with the behavior of particles at the smallest scales, where the classical rules of physics break down. In this realm, particles can exist in multiple states simultaneously, and their behavior can be described only probabilistically. The concept of time in quantum mechanics is particularly problematic. At the quantum level, time often appears to be irrelevant. When physicists describe systems of particles using equations such as the Schrödinger equation, time is just another variable, treated symmetrically with space. This is in sharp contrast to our everyday experience, where time seems to move in one direction only, from past to future. In quantum mechanics, the fundamental laws of physics are time reversible, meaning that they do not distinguish between past and future. This suggests that time's arrow, the irreversible flow of time that we experience, might not be a fundamental feature of reality, but instead an emergent property. The concept of time in quantum mechanics becomes even more complicated when we consider entanglement, a phenomenon in which two or more particles become linked in such a way that the state of one particle is instantaneously correlated with the state of another, no matter how far apart they are. This spooky action at a distance, as Einstein called it, challenges our understanding of both time and space. In entangled systems, the flow of time seems to become irrelevant. The relationship between particles does not depend on a linear sequence of events, suggesting that time might be less fundamental than previously thought. One of the most intriguing theories that challenges our conventional understanding of time is the block universe theory, also known as eternalism. This idea arises from Einstein's theory of relativity and suggests that time is not something that flows, but rather a dimension in which all events, past, present, and future, coexist simultaneously. In the block universe, the passage of time is an illusion created by our limited perspective. Imagine time as a landscape. When we stand at one point on this landscape, we experience that moment as the present. However, from a higher dimensional viewpoint, the entire landscape, the past, present, and future, is laid out all at once. Just as all points in space exist simultaneously, all points in time exist simultaneously. The past is not gone, and the future is not yet to come. They are simply parts of the space-time continuum, existing as part of a larger, unchanging whole. If the block universe is correct, then time does not flow in the way we perceive it. Our experience of time might be similar to watching a movie. We see the frames one after another and perceive motion, but in reality, the entire film exists at once. Our consciousness might be moving through time in a similar way, experiencing moments sequentially, even though they all coexist in the space-time block. Despite these radical ideas about time, we still experience the world as a sequence of events. A glass shatters, but it does not spontaneously reassemble. Ice melts, but does not freeze on its own. This irreversibility of time, the so-called arrow of time, is deeply rooted in the laws of thermodynamics, particularly the second law, which states that entropy, a measure of disorder, in a closed system always increases over time. Entropy provides a direction to time that seems absent in the fundamental laws of physics. While the equations governing the universe at a microscopic level are time reversible, meaning they could work equally well if time ran backward, the second law of thermodynamics introduces a preferred direction, from lower entropy to higher entropy. This gives rise to the arrow of time that we experience. However, some physicists argue that the arrow of time may itself be an emergent phenomenon, rather than a fundamental aspect of the universe. It could arise from the initial conditions of the universe, particularly the extraordinarily low entropy state at the moment of the Big Bang. If this is the case, then the arrow of time might be a consequence of the universe's birth rather than a fundamental feature of reality. This again raises the possibility that time, as we experience it, is not fundamental, but rather a product of the specific conditions of our universe. Philosophically, the notion that time may be an illusion has profound implications for our understanding of consciousness and existence. If time does not exist as we perceive it, then what does it mean to be conscious in a world where past, present, and future are indistinguishable? Some philosophers and neuroscientists suggest that our perception of time is closely tied to the way our brains process information. The brain constructs a continuous stream of consciousness by piecing together discrete moments of sensory input, much like a film projector creates the illusion of motion by rapidly displaying still images. In this view, time may be a mental construct, a way for our brains to make sense of the universe. Just as we perceive colors that do not exist outside our minds, color is merely the brain's interpretation of different wavelengths of light, we might perceive time as a flow when it is, in fact, static. This idea is bolstered by research into altered states of consciousness, such as meditation, psychedelic experiences, and certain neurological conditions, in which individuals report a breakdown of the usual perception of time. In these states, people often describe a sense of timelessness, or the feeling that past, present, and future are all one. Such experiences suggest that our perception of time is flexible and can be altered, reinforcing the idea that time might be a mental construct. Ultimately, the question of whether time is an illusion touches on some of the deepest mysteries of existence. If time does not exist as we perceive it, then our understanding of reality, causality, and even the nature of life and death might need to be re-evaluated. Time, in this view, could be akin to a trick of the mind, a useful but ultimately flawed way of organizing our experiences. Physicists continue to wrestle with the concept of time, seeking something called a theory of everything. Some suggest that such a theory might reveal that time, as we understand it, does not exist at the most fundamental level of reality. If this is true, then the implications for our understanding of the universe and our place in it are staggering. But what exactly is a theory of everything? Well, put simply, a theory of everything would encompass all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Today, we have two primary frameworks that describe these forces: general relativity, which accounts for gravity and large-scale structures like stars and galaxies, and quantum mechanics, which explains the behavior of particles at microscopic scales. However, these two theories are fundamentally incompatible. General relativity sees space and time as continuous, while quantum mechanics treats them as quantized and probabilistic. Bridging this gap is the central challenge for a theory of everything. Albert Einstein's general theory of relativity, formulated in 1915, revolutionized our understanding of gravity. In Einstein's view, gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time. Massive objects like stars and planets warp the fabric of space-time, causing other objects to move in response to that curvature. This insight replaced the Newtonian idea of gravity as a force acting at a distance and explained a variety of phenomena that Newtonian mechanics could not, such as the precise orbit of Mercury and the bending of light around massive objects, gravitational lensing. General relativity has been incredibly successful in describing large-scale phenomena, such as the dynamics of galaxies and the expansion of the universe. However, it breaks down at extremely small scales, particularly in describing the center of black holes or the conditions of the universe just after the Big Bang. At these scales, quantum effects become significant, and general relativity alone cannot provide a complete picture. Quantum mechanics, developed in the early 20th century by scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, provides a detailed description of the interactions between subatomic particles. Unlike general relativity, quantum mechanics deals with probabilities rather than certainties. The behavior of particles is governed by wave functions, which describe the probability of finding a particle in a particular state. This probabilistic nature is fundamentally different from the deterministic view of spacetime in general relativity. One of the triumphs of quantum mechanics is the Standard Model of particle physics, which unifies three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. The Standard Model successfully describes a wide range of particle interactions and has been confirmed through countless experiments. However, it does not include gravity, the fourth fundamental force, nor does it explain certain cosmological mysteries, such as dark matter and dark energy. The biggest obstacle to a theory of everything is gravity. While general relativity beautifully explains gravity at large scales, it doesn't work at quantum scales. When physicists try to apply quantum mechanics to gravitational fields, they encounter infinities, mathematical quantities that make no physical sense. This issue becomes especially critical in extreme environments, such as black holes, where both quantum effects and gravitational effects are significant. The mathematical incompatibility of gravity and quantum mechanics suggests that we are missing a deeper theory that can unify them. Physicists believe that gravity must have a quantum description, but no one has yet found a consistent theory that works in all situations. This has led to the search for new ideas, such as quantum gravity, which could unify general relativity and quantum mechanics under one framework. One of the most prominent attempts to develop a theory of everything is string theory. In string theory, the fundamental building blocks of the universe are not point particles, as in the Standard Model, but rather tiny, vibrating strings. These strings can vibrate in different ways, and the different patterns of vibration correspond to different particles. In this framework, gravity emerges naturally as one of the vibrational modes of the strings, thereby incorporating gravity into a quantum framework. String theory also introduces the concept of extra dimensions. While we are familiar with 3 dimensions of space and 1 dimension of time, string theory suggests that there may be additional hidden dimensions that are compactified, curled up so small that they are imperceptible to us. These extra dimensions could help explain why gravity is so much weaker than the other fundamental forces, as it may be spread out over these additional dimensions. However, string theory is far from proven. One of its major criticisms is that it is not experimentally testable in any practical sense. The energy scales required to probe the structure of strings are so high that they are beyond the reach of current or foreseeable technology. This has led some physicists to question whether string theory is truly a scientific theory, as it currently lacks the ability to make falsifiable predictions. Another approach to unifying gravity and quantum mechanics is loop quantum gravity. Unlike string theory, which attempts to replace point particles with strings, loop quantum gravity works directly with the fabric of spacetime itself. It proposes that spacetime is quantized at the smallest scales, forming a network of discrete loops. These loops form a kind of atomic structure of space, similar to how matter is made up of atoms. Loop quantum gravity has had some success in explaining certain phenomena, such as the behavior of black holes and the Big Bang. However, like string theory, it is not yet complete, and much work remains to be done before it can be considered a viable theory of everything. Any theory of everything must also account for 2 of the biggest mysteries in modern cosmology: dark matter and dark energy. Dark matter is one of the most critical ingredients in the universe, but it's something we cannot directly observe. It doesn't emit, absorb, or reflect light, which makes it invisible to telescopes. Instead, its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Without dark matter, many of the structures we see in the universe today, from galaxies to massive clusters of galaxies, would not have formed. The first hint of dark matter's existence came in the 1930s when Swiss astronomer Fritz Zwicky observed the Coma cluster, a collection of galaxies. Zwicky noticed that the galaxies in the cluster were moving much faster than expected based on the visible matter alone. To account for this discrepancy, he proposed the existence of missing mass, what we now refer to as dark matter. Further evidence came in the 1970s when astronomer Vera Rubin studied the rotation curves of spiral galaxies. Rubin found that stars at the outer edges of galaxies were moving just as fast as stars closer to the center, a puzzling result because, according to Newtonian mechanics, the stars on the outskirts should be moving slower if only visible matter was present. The explanation for this anomaly was that an unseen mass, dark matter, was providing the necessary gravitational pull to keep those stars moving at such high speeds. While dark matter has been established as a critical player in the universe's evolution, its composition remains a mystery. One prevailing theory suggests that dark matter is made of WIMPs, for weakly interacting massive particles. These hypothetical particles would interact with regular matter only through gravity and the weak nuclear force, making them difficult to detect. Despite several experiments designed to catch a glimpse of WIMPs, including underground detectors and particle accelerators like the Large Hadron Collider, LHC, none have yet provided definitive evidence. Another theory posits that dark matter could be composed of axions, ultralight particles that might also interact weakly with ordinary matter. Like WIMPs, axions have eluded detection, but ongoing experiments continue to search for them. There are also alternative explanations for dark matter's gravitational effects. Modified Newtonian dynamics, also known as MOND, is a theory that suggests the laws of gravity might need to be tweaked to explain galaxy rotation curves without invoking dark matter. However, MOND struggles to explain the full range of cosmological observations, such as the cosmic microwave background and the formation of large-scale structures in the universe, where dark matter plays a central role. Despite its invisibility, dark matter is essential to the universe's structure. It acts like an invisible scaffolding upon which galaxies form and grow. Without dark matter, the early universe's matter density wouldn't have been enough to pull together into galaxies and clusters through gravity alone. Furthermore, dark matter's gravitational effects are critical in the study of cosmic phenomena, like gravitational lensing, where massive objects bend light from distant sources. Observing these light-bending effects allows astronomers to map out where dark matter is located, even though it remains unseen. While dark matter explains the gravitational forces holding galaxies together, dark energy addresses a completely different mystery: the accelerating expansion of the universe. Rate. In the 1990s, two independent teams of astronomers were studying distant supernovae to measure the universe's expansion rate. They expected to find that the expansion was slowing down, as gravity from matter should be pulling everything back together. Instead, they found the opposite. The universe's expansion was accelerating. This was a shocking discovery, as it implied the existence of a new, unseen force that was pushing galaxies apart. To explain this unexpected acceleration, cosmologists introduced the concept of dark energy. However, dark energy is even more elusive than dark matter, and its nature remains largely speculative. One leading hypothesis is that dark energy is related to the cosmological constant, first introduced by Albert Einstein. In his theory of general relativity, Einstein included a term called the cosmological constant, which acted as a repulsive force to counteract gravity and keep the universe static. After Edwin Hubble's discovery of the expanding universe, Einstein abandoned the idea, calling it his greatest blunder. However, the discovery of the accelerating universe brought the cosmological constant back into play as a potential explanation for dark energy. In this context, dark energy could be thought of as a property of space itself. As space expands, the energy density associated with dark energy remains constant, leading to the universe's accelerated expansion. This model fits current observations well, but it leaves many questions unanswered. For example, why does dark energy have the value it does? If the cosmological constant were slightly different, the universe might have expanded too rapidly for galaxies to form, or it might have collapsed in on itself. Another possibility is that dark energy is related to a dynamic field known as quintessence, which evolves over time. Unlike the cosmological constant, quintessence would change its strength as the universe expands, potentially providing a more flexible explanation for dark energy's effects. Dark energy is the dominant component of the universe, making up about 68% of its total energy density. Its influence has become more significant over time as the universe expanded. In the early universe, dark matter and radiation played a more prominent role, but as space grew larger, dark energy began to dominate, driving the accelerating expansion we see today. Dark energy has profound implications for the universe's fate. If the acceleration continues indefinitely, the universe will keep expanding, causing galaxies to drift farther apart. Eventually, distant galaxies may become so far removed that their light can no longer reach us, plunging the universe into a big freeze where stars burn out, and all that remains are isolated black holes and cold remnants of once luminous galaxies. Put simply, together, dark matter and dark energy make up about 95% of the universe's total content, but we know very little about their true nature. Neither dark matter nor dark energy is explained by the Standard Model or by general relativity, which suggests that our current understanding of the universe is incomplete. A true theory of everything must not only unify gravity with quantum mechanics, but also explain the existence and behavior of dark matter and dark energy. Thus, despite the progress made in theoretical physics over the past century, the quest for a theory of everything remains unfinished. Some physicists believe that new experimental discoveries, perhaps from high-energy particle colliders or precision measurements of cosmological phenomena, will provide the missing pieces of the puzzle. Others suggest that the very framework of physics may need to be radically rethought, requiring new concepts that go beyond space, time, and matter as we currently understand them. In the end, whether or not such a theory will ever be found remains an open question, but the pursuit itself has already deepened our understanding of the universe and our place within it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
About quark gluon plasma?
That's bad. That's bad for physics. For the cosmic microwave background, the leftover radiation from the Big Bang.
But you would like something.
NASA has been at the forefront of space exploration and scientific discovery for decades. Its relentless pursuit of knowledge has unveiled a series of discoveries that have profoundly altered our understanding of the universe. From distant galaxies and black holes to the early moments after the Big Bang, NASA's missions have expanded the horizons of human knowledge, challenging existing paradigms and fostering new theories. Join us in today's episode as we dig deep into the most significant discoveries that have reshaped our comprehension of the cosmos. Number 1. The cosmic microwave background radiation, the afterglow of creation. One of NASA's most significant contributions to cosmology is the discovery and mapping of the CMB, for cosmic microwave background radiation. The CMB is the faint afterglow of the Big Bang, the primordial explosion that gave birth to the universe approximately 13.8 billion years ago. This discovery provided critical evidence supporting the Big Bang theory, fundamentally altering our understanding of the universe's origins. The CMB was first detected by accident in 1965 by Arno Penzias and Robert Wilson, who won the Nobel Prize in Physics for their work. However, it was NASA's Cosmic Background Explorer, COBE, satellite, launched in 1989, that provided the first detailed map of the CMB. COBE's data confirmed that the CMB was almost perfectly uniform across the sky, with tiny fluctuations that represented the seeds of all the current structures in the universe, such as galaxies and clusters of galaxies. These tiny fluctuations in the CMB provided crucial insights into the early universe's conditions, helping to refine the Big Bang theory and leading to a better understanding of the universe's age, composition, and development. The COBE mission was followed by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, both of which provided even more detailed measurements of the CMB. These missions allowed scientists to determine that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, a mysterious force driving the universe's accelerated expansion. The discovery and study of the CMB have been foundational in cosmology, providing a baby picture of the universe that has shaped our understanding of everything from the nature of matter and energy to the ultimate fate of the cosmos. Number 2. The accelerating expansion of the universe, unveiling dark energy. In the late 1990s, one of the most groundbreaking discoveries in astronomy was made using data from NASA's Hubble Space Telescope. Scientists found that the expansion of the universe is not slowing down, as previously thought, but is actually accelerating. This discovery was a complete surprise and led to the introduction of the concept of dark energy, a mysterious force that permeates all of space and is driving the universe's accelerated expansion. The discovery was made by observing distant Type Ia supernovae, which are exploding stars that can be used as standard candles to measure distances in the universe. By comparing the brightness of these supernovae at different distances, scientists found that distant galaxies were moving away from us faster than nearby ones, indicating that the universe's expansion rate was increasing over time. The implications of this discovery are profound. Dark energy, which is believed to make up about 68% of the universe, remains one of the biggest mysteries in modern physics. Its discovery has led to a fundamental shift in our understanding of the universe, suggesting that the cosmos could continue expanding forever, potentially leading to a big freeze where galaxies drift apart, stars burn out, and the universe becomes a cold, dark place. NASA continues to study dark energy through various missions, including the upcoming Nancy Grace Roman Space Telescope, which aims to explore the nature of dark energy by measuring the distribution of galaxies across cosmic time. The discovery of dark energy is a testament to the unexpected ways the universe continues to surprise us, challenging our theories and pushing the boundaries of our knowledge. Number 3. The discovery of exoplanets, expanding the search for life. One of the most exciting and transformative discoveries made by NASA in recent decades is the detection of exoplanets, planets orbiting stars outside our solar system. This search was revolutionized by NASA's Kepler Space Telescope, launched in 2009, which was designed to monitor over 150,000 stars in a small patch of the Milky Way galaxy. Kepler's mission was to look for tiny dips in a star's brightness that occur when a planet passes in front of it. a method known as the transit method. Kepler's results were astonishing. The telescope discovered over 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. These discoveries revealed that planets are not rare, but are common throughout the galaxy, with estimates suggesting that there are more planets than stars in the Milky Way. Among these exoplanets, several have been found in the habitable zone of their stars, the region where conditions might be right for liquid water to exist on a planet's surface, which is considered a key ingredient for life. One of the most famous of these is Kepler 186, an Earth-sized planet located in the habitable zone of its star. This discovery has profound implications for the search for extraterrestrial life, suggesting that there may be billions of potentially habitable worlds in our galaxy alone. The discovery of exoplanets has opened up a new field of astronomy, with NASA continuing to lead the search for life beyond our solar system. The Transiting Exoplanet Survey satellite, also known as TESS, launched in 2018, is continuing Kepler's work by surveying the entire sky for exoplanets. Meanwhile, the James Webb Space Telescope, JWST, launched in 2021, is poised to study the atmospheres of these distant worlds in unprecedented detail, searching for signs of life. The discovery of exoplanets has fundamentally changed our understanding of the universe, revealing that our solar system is just one of countless planetary systems scattered throughout the galaxy. It has also reignited the age-old question: are we alone in the universe? NASA's ongoing search for exoplanets and the conditions for life continues to bring us closer to answering this question. Number 4. The observation of gravitational waves, a new window into the universe. In 2015, scientists made the first direct observation of gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, such as the collision of black holes. This discovery, which confirmed a major prediction of Albert Einstein's theory of general relativity, was made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a project with significant contributions from NASA. Gravitational waves were first predicted by Einstein in 1915 as part of his theory of general relativity, which describes gravity as the warping of space and time by massive objects. However, detecting these waves proved to be an enormous challenge due to their incredibly faint nature. LIGO, which consists of 2 facilities in the United States, was designed to detect these minuscule ripples by measuring the tiny distortions they cause as they pass through Earth. The first detection of gravitational waves came from the merger of 2 black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. This event was named GWW15914 and marked the beginning of a new era in astronomy, gravitational wave astronomy. The ability to detect and study gravitational waves has opened up a completely new way of observing the universe. Unlike light, gravitational waves are not easily absorbed or scattered, allowing them to carry information about the most violent and energetic events in the cosmos, such as black hole mergers, neutron-star collisions, and even events from the early universe. Since the first detection, LIGO, along with its European counterpart Virgo, has detected dozens of gravitational wave events, providing new insights into the nature of black holes, the structure of neutron stars, and the behavior of matter under extreme conditions. These observations have confirmed that black holes are common throughout the universe and have provided a new way to test the limits of Einstein's theory. Looking ahead, NASA is collaborating on LISA for the Laser Interferometer Space Antenna, a space-based gravitational wave detector that will be sensitive to a different range of gravitational waves than LIGO, potentially revealing new physics and shedding light on the most mysterious phenomena in the universe. Number 5. The exploration of Mars, searching for life on the red planet. NASA's exploration of Mars has been one of its most enduring and scientifically rewarding endeavors. Since the 1960s, NASA has sent a series of missions to Mars, each more sophisticated than the last, culminating in the recent Mars rovers, such as Curiosity and Perseverance, which have transformed our understanding of the red planet and its potential to host life. One of the most groundbreaking discoveries on Mars came from the Curiosity rover, which landed in Gale Crater in 2012. Curiosity found evidence that Mars once had conditions suitable for life, including ancient riverbeds, lakes, and the presence of key chemical ingredients for life, such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Curiosity also detected complex organic molecules in Martian soil, which, while not proof of life, are the building blocks of life as we know it. The Perseverance rover, which landed in Jezero Crater in 2021, is continuing this search for life. Jezero Crater was chosen as the landing site because it is believed to have once been a lake, with river deltas that could have preserved signs of ancient microbial life. Perseverance is equipped with advanced scientific instruments to analyze rocks and soil, searching for biosignatures, chemical or physical signs of past life. One of Perseverance's most ambitious goals is to collect samples of Martian rock and soil that will be returned to Earth by a future mission. This will allow scientists to study Martian material in unprecedented detail, potentially providing the first direct evidence of life beyond Earth. NASA's Mars exploration program has not only provided evidence that Mars was once habitable, but it has also laid the groundwork for future human exploration. For example, the discovery of water ice on Mars suggests that future astronauts could extract water for drinking and producing oxygen and rocket fuel, making long-term human missions to Mars feasible. As NASA prepares for the next steps in Mars exploration, including the potential human exploration of Mars in the 2030s, the discoveries made by missions like Curiosity and Perseverance will continue to be a vital foundation for our understanding of the red planet and its potential to support life. Number 6. The structure of the Milky Way. For centuries, the true shape and extent of the Milky Way remained elusive due to our position within it. However, through the use of advanced telescopes and space missions, NASA has unveiled the intricate details of the galaxy's architecture. The Milky Way is a barred spiral galaxy, characterized by a central bar-shaped region of stars and a disk composed of several spiral arms. These spiral arms, filled with gas, dust, and young stars, wind out from the central bulge, which houses older stars and a supermassive black hole known as Sagittarius A. The galaxy's disk is relatively thin, but it extends for about 100,000 light-years across, with the Sun located about 26,000 light-years from the galactic center, nestled in the Orion Arm. One of the most significant breakthroughs in mapping the Milky Way came from the NASA-led Cosmic Background Explorer, or COBE, and later, the Spitzer Space Telescope. COBE helped confirm the Milky Way's spiral structure by detecting the distribution of stars and dust in infrared light, which penetrates the dense interstellar dust that obscures visible light. Spitzer further refined this view, revealing the intricate details of the galaxy's arms and confirming the presence of the central bar. In addition, NASA's WMAP and the European Space Agency's Gaia mission have provided crucial data about the Milky Way's shape and size. Gaia, in particular, has mapped the positions and motions of over 1 billion stars, giving astronomers an unprecedented 3D view of the galaxy. This data has helped confirm that the Milky Way is not a simple disk, but has a warped shape, likely caused by interactions with neighboring galaxies, such as the Sagittarius Dwarf Galaxy. Moreover, NASA's Fermi Gamma Ray Space Telescope has uncovered evidence of massive bubbles of high-energy radiation extending above and below the Milky Way's disk. These Fermi bubbles, are thought to be remnants of an energetic event in the galaxy's past, possibly linked to activity from Sagittarius A. NASA's efforts to map and understand the structure of the Milky Way have not only expanded our knowledge of our galaxy, but have also provided insights into the processes that shape galaxies across the universe. This research continues to evolve, offering new glimpses into the dynamic and ever-changing nature of the Milky Way. Number 7. The exploration of the outer solar system. NASA's Voyager exploration of the outer solar system represents one of the most ambitious and successful endeavors in the history of space exploration. Launched in 1977, Voyager 1 and Voyager 2 were initially designed to take advantage of a rare planetary alignment that allowed them to visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, using gravity assists to propel them from one destination to the next. This grand tour of the solar system provided humanity with its first close-up views of these distant worlds, fundamentally changing our understanding of the outer planets and their moons. Voyager 1 was the first of the two spacecraft to launch and quickly became the first human-made object to fly by Jupiter in 1979. The data it sent back revealed the planet's turbulent atmosphere, with its great red spot, a massive storm larger than Earth, and its complex system of moons. Particularly significant was the discovery of active volcanoes on Io, one of Jupiter's moons, making it the first body beyond Earth known to be volcanically active. Voyager 1 then proceeded to Saturn in 1980, where it captured detailed images of the planet's rings and discovered new moons. It also provided a closer look at Titan, Saturn's largest moon, revealing its thick atmosphere, which scientists believe might harbor conditions similar to early Earth. Voyager 2 followed a similar path, but went on to achieve what no other spacecraft has done. It visited Uranus in 1986 and Neptune in 1989. The flyby of Uranus uncovered a magnetic field tilted at a bizarre angle and 11 new moons. Voyager 2's encounter with Neptune provided the first images of the planet's dynamic atmosphere, including the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, and the discovery of geysers on Triton, Neptune's largest moon. After completing their primary missions, both Voyager spacecraft continued on their paths out of the solar system, with Voyager 1 becoming the first spacecraft to enter interstellar space in 2012, followed by Voyager 2 in 2018. As of 2024, Voyager 1 is about 15 billion miles from Earth, and Voyager 2 is around 13 billion miles. These distances are vast, but the twins still send data back to Earth by using their onboard instruments and radio communication systems. The signals they send take over 20 hours to reach Earth, traveling at the speed of light. Despite their distance, the spacecraft continue to transmit valuable scientific information about the space environment they encounter as they journey through the outer reaches of the solar system and into interstellar space. The data they send back is helping scientists learn more about the heliosphere, the protective bubble created by the sun's solar wind, and the interstellar medium beyond it. This information is crucial for understanding how our solar system interacts with the surrounding galaxy and provides a glimpse into the conditions of interstellar space, a region that has remained largely unexplored until now. Number 8. The Hubble Deep Field and the Evolution of Galaxies. The Hubble Deep Field represents one of the most profound observational campaigns in the history of astronomy. Conducted by the Hubble Space Telescope in 1995, this initiative aimed to peer into the farthest reaches of the universe, revealing a patch of sky in the constellation Ursa Major that was seemingly empty and devoid of stars or galaxies. Over 10 consecutive days, Hubble captured light from this tiny region, about 1/24 of the sky, creating an image that forever changed our understanding of the universe. The Hubble Deep Field revealed a staggering number of galaxies, nearly 3,000, in a minuscule portion of the sky. These galaxies varied greatly in shape, size, and color, indicating a broad spectrum of ages and evolutionary stages. Some of the galaxies were relatively close to Earth, while others were billions of light-years away, meaning Hubble was capturing images of these galaxies as they appeared when the universe was just a fraction of its current age. This unprecedented glimpse into the early universe offered astronomers crucial insights into the evolution of galaxies. The Hubble Deep Field provided a timeline that spanned billions of years, showing how galaxies have changed over cosmic time. Some of the most distant galaxies in the Hubble Deep Field were small and irregular, suggesting that they were in the early stages of formation. This observation supports the theory that galaxies began as small structures that merged and grew into the massive galaxies we see today, like the Milky Way. Moreover, the diversity of galaxies observed in the Hubble Deep Field, from spirals to ellipticals to peculiar shapes, helped scientists piece together the processes that drive galaxy evolution. For instance, the presence of blue, star-forming galaxies alongside older, redder galaxies indicated that star formation was more rampant in the early universe and has since slowed down. The Hubble Deep Field also highlighted the importance of dark matter in galaxy formation. The distribution and interaction of galaxies in the field suggested that dark matter played a crucial role in their evolution, influencing their shapes and the rate at which they merged with others. Overall, the Hubble Deep Field provided a window into the universe's distant past, offering a profound understanding of how galaxies evolve over time. It set the stage for future deep-field observations and remains a cornerstone in our quest to understand the origins and fate of galaxies in the cosmos. Number 9. The exploration of the Kuiper Belt and the discovery of Pluto's geology. The Kuiper Belt, a distant and icy region of the solar system, represents one of the last frontiers of planetary exploration. Located beyond Neptune's orbit, this vast donut-shaped disk is home to countless icy bodies, dwarf planets, and remnants from the early solar system. First proposed by astronomer Gerard Kuiper in 1951, the Kuiper Belt was hypothesized as a region containing small, icy bodies left over from the solar system's formation. It wasn't until the early 1990s that the first Kuiper Belt object was discovered, confirming the existence of this distant region. The Kuiper Belt extends from about 30 to 55 astronomical units from the Sun, with its objects composed primarily of frozen volatiles such as water, ammonia, and methane. The discovery of the Kuiper Belt provided critical insights into the origins of short-period comets and the early solar system's formation processes. As a reservoir of ancient material, the Kuiper Belt holds the potential to reveal secrets about the solar system's birth and the processes that led to the formation of planets. The most significant milestone in the exploration of the Kuiper Belt came with NASA's New Horizons mission. Launched in 2006, New Horizons was the first spacecraft designed to explore this distant region, with its primary target being Pluto, the most famous of the Kuiper Belt's inhabitants. After a journey of nearly a decade, New Horizons made its historic flyby of Pluto in July 2015, providing humanity with its first close-up images and data from this enigmatic dwarf planet. The flyby revealed Pluto as a complex and geologically active world, shattering previous assumptions that it was a frozen, inert body. New Horizons sent back images of towering mountains of water ice, vast plains of nitrogen ice, and signs of cryovolcanism. The mission's success highlighted the importance of exploring the Kuiper Belt, showing that even at the solar system's fringes, planetary bodies could be dynamic and diverse. Following its successful flyby of Pluto, New Horizons continued its journey deeper into the Kuiper Belt. On January 1, 2019, it made a close approach to another Kuiper Belt object, Arrokoth, previously known as 2014 MU-69. This small, bilobed object provided scientists with a glimpse into the early solar system's building blocks. Arakoth's shape and surface features suggested that it formed through the gentle merging of two smaller bodies, providing valuable insights into how planets and other solar system bodies might have formed. The exploration of Arakoth and other Kuiper Belt objects has deepened our understanding of the Kuiper Belt as a repository of primordial material. These objects have remained largely unchanged since the solar system's formation, preserving the conditions of the early solar nebula. By studying them, scientists can gain a clearer picture of the processes that led to the formation of planets and the evolution of the solar system. On the other hand, note that the exploration of the Kuiper Belt is still in its early stages, with much left to discover. Future missions could target other Kuiper Belt objects, including larger and more distant objects, to further unravel the mysteries of this remote region. The Kuiper Belt also presents a valuable opportunity to study the formation of planetary systems in other star systems, as it shares similarities with the debris disks observed around young stars. Moreover, the continued exploration of the Kuiper Belt has implications for our understanding of the solar system's boundaries. The region marks the transition from the solar system's planetary zone to the more distant and diffuse Oort cloud, the source of long-period comets. Understanding the Kuiper Belt's structure and population is key to comprehending the solar system's architecture and its interaction with the interstellar environment. Number 10. The first images of black holes and the Event Horizon Telescope. Black holes has long fascinated scientists and the public alike, largely because of the enigmatic nature of their cosmic giants. They are regions of space-time where gravity is so intense that nothing, not even light, can escape. This makes them invisible against the backdrop of space, but their presence can be inferred from their effects on nearby matter and radiation. A groundbreaking tool in the study of black holes has been the Event Horizon Telescope, also known as EHT, an international collaboration that aims to capture images of these elusive objects. It could be said that the EHT represents a monumental leap forward in observational astronomy. The project began in earnest in 2012, bringing together over 200 researchers from institutions worldwide with the goal of imaging the event horizon of a black hole. The EHT is not a single telescope, but a network of radio telescopes located at different points around the globe. By synchronizing these telescopes through a technique called very long baseline interferometry, the EHT effectively creates a planet-sized observatory with unprecedented resolution. The EHT's first major achievement was the release of the image of the supermassive black hole in the galaxy M87 in April 2019. This was a historic moment in astrophysics, as it provided the first direct visual evidence of a black hole's existence. The image showed a bright ring-like structure with a dark central region representing the shadow of the black hole against the glowing gas and plasma surrounding it. This groundbreaking result confirmed many predictions of general relativity and provided new insights into the structure and behavior of black holes. The success of the EHT then has paved the way for further explorations into the nature of black holes. Future improvements in the array, including the addition of more telescopes and the use of higher frequency observations, are expected to enhance the resolution and detail of the images. Upcoming observations will focus not only on refining the image of M87's black hole, but also on imaging the event horizon of the black hole at the center of our own Milky Way galaxy, known as Sagittarius A. Additionally, the EHT's findings are likely to have broader implications for our understanding of fundamental physics. For example, studying the behavior of matter and radiation near the event horizon may provide insights into the nature of space-time, the formation of black holes, and the processes governing their growth and interactions with their surroundings. In summary, the study of black holes and the contributions of the Event Horizon Telescope represent a profound leap in our understanding of the universe. By capturing images of these cosmic behemoths, the EHT has provided a direct glimpse into regions that were previously beyond the reach of observational astronomy, opening up new avenues for research and deepening our understanding of the most extreme objects in the cosmos. Number 11. The James Webb Space Telescope and the Early Universe. The James Webb Space Telescope has opened a new era of cosmology. Launched on December 25, 2021, Webb's advanced capabilities have significantly transformed our comprehension of the early universe, providing unprecedented insights into the cosmos's infancy. At its core, Webb's ability to peer deep into the universe is facilitated by its large, segmented mirror and its position in orbit around the second Lagrange point, about 1.5 million kilometers from Earth. This strategic location, combined with its infrared-optimized instrumentation, allows the telescope to observe the faintest and most distant objects in the universe, those that were previously beyond the reach of earlier telescopes like Hubble. One of the most groundbreaking contributions of James Webb is its capability to observe the universe's first galaxies. By looking back in time through the infrared spectrum, the telescope can detect the light from the earliest galaxies that formed shortly after the Big Bang, about 13.8 billion years ago. These observations have provided new insights into the formation and evolution of the first galaxies, revealing that galaxy formation occurred much earlier than previously thought. For instance, James Webb has identified galaxies formed only a few hundred million years after the Big Bang, challenging previous models of galaxy evolution and pushing the boundaries of our knowledge about how these structures emerged. Webb's deep-field observations have also shed light on the process of reionization, a pivotal era in the universe's history when the first stars and galaxies ionized the intergalactic medium. This period marked the transition from the cosmic dark ages to a universe filled with light. By examining the distribution and characteristics of early galaxies, James Webb has provided crucial data on the timing and nature of reionization, offering a more detailed picture of how the first cosmic structures interacted with their surroundings and contributed to the reionization of the universe. Moreover, the observatory has made significant strides in understanding the formation of stars and planetary systems. Its high-resolution infrared imaging allows scientists to observe star-forming regions obscured by cosmic dust, revealing previously hidden details about the birth of stars and the formation of protoplanetary disks. These observations are crucial for understanding the processes that lead to the formation of planetary systems, including our own. By studying these early star-forming regions, James Webb helps bridge the gap between the initial formation of stars and the eventual development of planetary systems, offering insights into the conditions that might lead to habitable planets. Another critical aspect of James Webb's mission is its ability to study the physical and chemical properties of the early universe. Through its advanced spectroscopic capabilities, the Webb telescope can analyze the light from distant galaxies and stellar objects to determine their composition, temperature, and other fundamental properties. This information is vital for understanding the chemical evolution of the universe, including the formation of heavy elements and the enrichment of the interstellar medium. By examining the spectral signatures of early galaxies and stars, James Webb provides a detailed account of how these objects contributed to the chemical makeup of the universe. In addition to its observational capabilities, findings made by James Webb have prompted a re-evaluation of theoretical models of cosmic evolution. Its data has led to new hypotheses about the formation and growth of galaxies, the nature of dark matter, and the conditions that led to the development of complex structures in the universe. These insights are reshaping our understanding of cosmological processes and prompting revisions to existing models of the early universe. The impact of James Webb extends beyond the immediate realm of galaxy and star formation. Its observations have provided a broader context for understanding the fundamental processes that shaped the universe's structure. By offering a clearer picture of the early universe, the Supreme Observatory helps scientists address some of the most profound questions in cosmology, including the nature of dark energy, the formation of the first black holes, and the origins of cosmic inflation. In summary, thanks to its advanced observational capabilities and infrared technology, the Premier telescope has dramatically enhanced our knowledge of the cosmos's infancy. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.